Okay, so we're going to talk about um, transition metals as catalysts. Um, Very early on in the topic, one of the characteristics of transition metals and their compounds is that they tend to be good catalysts. Right, now we can subdivide these into homogeneous, which we're going to talk about today. And this is when you have the reactants and the products are in the same, the reactants and the catalyst are in the same phase. Usually they are in aqueous solution. So you've got the catalyst in aqueous solution and the reactants are aqueous solution. Heterogeneous is when they're in different phases. And we're not going to talk about them in this video. So that's usually the case when you've got like the catalyst is a solid with a large surface area, and the reactants are gases, and the products usually are gases as well. So we're not going to talk about heterogeneous, we're going to talk about homogeneous in this video. Right, so one of the reactions which is actually on the specification is the reaction between this stuff, S2O8 minus, which is it's called the peroxidosulfate ion. The name is a clue. It's got some peroxide oxygens in there, so some of the oxygens are forming oxygen-oxygen single bond, and that's important because it means, well, if they've got oxidation numbers of -1, those oxygens. If you worked out the oxidation number of sulfur there, and you presume the oxygens were all -2, you'd find out the oxidation number of sulfur was +7. And that's impossible because sulfur can only have an oxidation number of maximum of +6 because it's only got 6 electrons in its outer shell. So +7 would be impossible. And that's it's because the oxygens are peroxide oxygens. Anyway, that's besides the point really. But anyway, that peroxidosulfate is a fairly good oxidizing agent, and it will oxidize iodide ions to iodine, and you get 2 sulfate ions, gets reduced to the sulfate ion. Okay, now that's got a slow rate of reaction because the activation energy is high. EA activation energy is high, and the reason for that is these are both negatively charged species, so that it's going to be hard for them to collide with each other. They're going to repel. Okay, now we find that this reaction is catalyzed by iron 2+ ions or by iron 3+ ions. And this is how homogeneous catalysts always work, is that these basically act as electron carriers. So if you get Fe2+, it can accept an electron, it can give away an electron, I beg your pardon, and turn into Fe3+. And then Fe3+ can accept an electron and turn back into Fe2+. This is what the catalyst does. It goes round and round in this circle, okay, passing electrons from one thing to another. Now, if you do biology, that may be reminiscent of the electron transfer chain in mitochondria, and that's because that's exactly what's happening there. You've got a series of and some of them actually do contain Fe atoms. You've got a series of species which can be oxidized and reduced, and they can pass electrons, pick up electrons off something, pass them on to something else. Right, so in this reaction, the Fe2 and the Fe3 act as kind of middlemen for electrons, allowing the electrons to be transferred between these two things without them actually having to collide with each other. Right, so what we're going to do is we're going to break that equation down into the two separate half equations first of all. So that would give us, let's do the peroxidosulfate is going to go to SO4 2-. We need to balance the sulfurs there. Don't need to do anything with the oxygens, they're all balanced. No hydrogens to worry about. So we just need to balance the charges. Now we've got -4 on this side and only -2 on that side. So we need 2 electrons there. So they're gaining electrons, the peroxidosulfate ions, and getting reduced. Now let's do the other half of that is the iodine. So we're going to have 2I- are going to go to I2. Each I- is going to lose an electron. So just balance the charges, so it's going to be plus 2e minus on that side. Now let's have a look at this one here. Right, we're gaining 2 electrons. Now let's get rid of those electrons and cross them out. Instead of electrons, let's say they are being provided by Fe2+. Each Fe2+ can give an electron away. So we've got 2 Fe2+ there. And when they've given their electrons away, those Fe2+, they're going to turn into Fe3+. So that's one equation there. Now, and this one here, the iodide, well, they're going to give away the electron there. They could give it to an Fe3+. You need 2 of them. Cross those electrons off. They're not going to be free electrons. They're going to be passed on. So the Fe3+ will turn into Fe2+ in the process. Okay, so what's happening is this. If you combine those 2 equations together, you can see that all the Fe species will all just cancel out, because that's just acting as a catalyst. It doesn't permanently change. And you can see that the iron is acting as a middleman for the electrons. So it takes here the first equation, it gives electrons to the peroxide of sulfate, and in the second one it accepts electrons from the iodide, and it saves the 2 negatively charged species from having to collide with each other, and the iron just flips back and forth between the +2 and the +3 oxidation states. So in an exam they're very likely to say, right, here's this equation, here's this equation, and they'll say rewrite it as 2 separate equations showing how it can be catalyzed by Fe2+ or Fe3+. So the procedure is break it down into half equations, which you should be pretty good at doing that, and then get rid of the electrons by replacing them with the correct iron species. Now when I do these, I always get a bit confused. Is it Fe2+ or Fe3+? There's a little way of checking you've done it the right way. You just at the end, when you get the equation, so let's do this equation here. Yeah, just add up all the charges, and it should be the same on both sides if you've got the correct iron there. So we've got 2 minus and 2 times 2 plus 4 plus. So that's going to be +2 on that side of the equation. Here we've got 2 times 3 plus, so that's +6, and then take away 2 times 4, take away 4 minus, so that's going to be +2 on that side. So everything's okay. You've got the correct iron species on both sides of the equation. Okay, we're going to do another reaction there now, and this is the oxidation of alcohol, say ethanol, CH3CH2OH, and it can be oxidized by oxygen in aqueous solution to ethanoic acid, and you get water. Okay, and you check all that, you'll find I think that's balanced. Yeah, it is balanced. Yep, that's fine. Okay, so that equation is catalyzed either by cobalt 2+ ions or by cobalt 3+ ions. Incidentally, this reaction is not on the specification. They asked it in a past paper a few years ago, and we're just going to do exactly the same thing with this equation as we did with the peroxide of sulfate example. Right, so what we're going to do is we're going to rewrite this as 2 half equations. Okay, so the ethanol is oxidized. If you work out the oxidation number there, I think you can see in ethanol the oxidation number is well, let's see, sigma oxidation numbers is equal to the charge. So we've got 2 carbons, we don't know the oxidation number there. We've got 6 hydrogens, they're all +1, +6. We've got an oxygen which is always -2, that's equal to 0. So therefore we get 2C is equal to plus 4 is equal to 0, so that means carbon has got an oxidation number of -2 there. And the oxidation number of carbon in ethanoic acid, let's do that one. So sigma oxidation numbers is equal to the charge, sigma the sum. So we've got 2 carbons to worry about. We've got 4 hydrogens there, all +1. And we've got 2 oxygens, they're -2, so -4. That's equal to 0. So we can see the oxidation number of carbon there must be 0. So it's been oxidized, yeah. Here the oxidation number of oxygen is 0. And of course in oxygen, in water, it's -2. So the oxygen has been reduced. So anyway, let's split that into the 2 half equations. So here's our ethanol. Goes to ethanoic acid. Balance for oxygens, well, we need another oxygen on the left, so that's an H2O there. Then balance for hydrogens, well, we've got 4 hydrogens on the right and 8 on the left, so we need 4H plus. Balance for charges, we've got 4E minus there. Okay, so that's one half equation. And let's do the oxygen half equation, where we've got O2, and that's going to go to H2O. We need to balance, put a 2 there for the to balance the oxygens. Then we're going to need 4H plus here. And then for charges, we've got 0 charge on the right and +4 on the left, so we need 4 electrons there. Okay, so those are 2 half equations, and if you combine those 2 together, they're both 4 electron processes, so you don't have to do any multiplying, and you find that the hydrogen ions will cancel out, one of the waters will cancel out, and you will get that equation there. So it's nothing funny going on, everything works out okay. Right, now what we need to do is we need to replace electrons in these equations with cobalt species. Okay, so let's do this one here. The oxygen is gaining electrons. Now, what can give away electrons? So it's the it's the CO2 plus species which can give away the electrons. So let's cross out those electrons, and we want 4 CO2 plus, they're going to provide the electrons, and when they go to the other side they've lost the electrons, so that's now 4 CO3 plus. Okay, and then let's do this top equation. Well, instead of having electrons coming off here, we are going to get cobalt 2 plus is being made, so we want 4 CO2 plus there, and we want 4 CO3 plus on this side. The CO3 plus ions are oxidizing the alcohol. Okay, if you then recombine those 2 half equations, those 2 equations together, you will see that all the cobalt species cancel out, and you end up with this equation here, the overall equation. So exactly the same procedure as last time. Write 2 half equations, get rid of the electrons by putting in the 2 plus ions and the 3 plus ions of cobalt or iron, whichever one is the catalyst, and you've done that. Right, now our final example is mentioned on the specification, and this is we're quite familiar with this reaction. We're talking about here the oxidation. We're using titration equations. The oxidation of the ethane dioate ions by acidified manganate ions, purple manganate ions, which usually goes in the burette in your redox titrations. So the equation for that is 2MnO4 minus, and you need 16H plus, 5 ethane dioate ions, and that will go to 2 manganese 2 plus, you get 8H2O, and all of the ethane dioate ions are oxidized to carbon dioxide, so you're going to get 10 carbon dioxides there. So that's a tricky equation to balance. Okay, now this reaction is actually catalyzed, it's autocatalytic, and that means that it is catalyzed by one of its products, and the product which catalyzes is Mn2 plus, and it works, the way it works is it flips between the Mn2 plus state and the Mn3 plus ion, okay, just in the same way as the iron or the cobalt did in the previous two reactions. So we're going to write down the half equations. We're going to split this into two half equations and then replace the electrons with either of these two species to show the two reactions that are happening. You may remember actually when you do a manganate against ethane dioate titration, you actually have to, this stuff you put in the conical flask, and you have to heat up the conical flask at the start of the titration because the reaction is really slow because you haven't got any of this catalyst about. By the time you get to the end point, you don't need to heat it up because it's going quite quickly because you've got loads of catalyst about, loads of Mn2 plus, so it goes pretty quickly. You may remember that. Right, let's split this into two half equations then. So the two half equations are, you're going to have 2 MnO4 minus goes to 2 Mn2 plus. So we're going to need to balance oxygen, so we need 8 H2O on that side, and that means we need 16 H plus there. Do all your balance your charges, you'll find you're going to need 10 electrons there, 10 E minus. Let's do the ethane dioate. So you've got 5 C2O4, move it down a little bit, 5 C2O4 2 minus, and we want 5 CO2, that's going to go to the carbon dioxide, 10 CO2s. We don't need to balance any oxygens or hydrogens there, we just need to balance the charges, so you want 10 electrons on the right hand side. Right, so let's now replace the electrons with either our Mn2 plus species or Mn3 plus. Now, let's get rid of those electrons. What can provide electrons? Is it the 2 plus or the 3 plus? It's the 2 plus, so we want 10 Mn2 plus there. And that means on this side you are going to make 10 Mn3 plus. Right, let's do this one. Now we are going to oxidize the ethane dioate ions, and we want them to lose 10 electrons. So that means we're going to need 10 Mn3 pluses. They're going to remove 10 electrons from the ethane dioate. On this side, cross them out, you're going to have 10 Mn2 plus instead. Now, if you combine those two equations, you will find that all the Mn3 plus species all cancel out, and you're just left with two of those Mn2 pluses, because I say this one is a little bit different because it's autocatalytic, because it's catalyzed by the Mn2 plus, flipping backwards and forwards between Mn2 plus and Mn3 plus. Okay, we'll leave that one there, I think.